Hello everyone, my name is Bogdan Kostić and I will present to you now our paper Same Meaning, Different Scores, Lexical and Syntactic Sensitivity in LLM Evaluation, published at LREC 2026. This is a joint work with Connor Fallon, Julian Risch and Alexander Löser and a collaboration between DeepSet and the Berliner Hochschule für Technik. Let's start with the core problem and our motivation for this work. The rapid proliferation of LLMs has made standardized benchmarks the primary tool for model comparison. Public leaderboards have become the default instrument for model selection. They drive research directions, commercial adoption, and funding decisions. But there is a growing concern that these metrics may overestimate true generalization capabilities. Part of the worry comes from potential data leakage, where benchmark test sets leak into vast, often undisclosed training corpora. But more fundamentally, prior work has shown that LLM performance is remarkably sensitive to superficial variations in the input prompt. For example, studies have demonstrated that adding irrelevant context, reordering premises in reasoning tasks, or even changing the symbols used for answer choices can significantly alter model performance. However, these studies often don't distinguish between different kinds of linguistic changes. This leads us to the central question of our paper. Are benchmarks measuring reasoning, or just how well a model overfits to specific phrasing? More precisely, is the observed variance driven more by lexical shifts, this is changes in word choice, or by syntactic changes, meaning alterations in sentence structure? Let me give you the short version of our findings before diving into the details. First, we show that LLMs rely on surface lexical cues over abstract syntactic structure. Models are significantly more sensitive to synonym substitution than to grammatical restructuring. Second, we demonstrate that benchmark leaderboards are brittle. Minor meaning-preserving changes are sufficient to alter model rankings, challenging the reliability of static leaderboards. Third, we find that model scaling does not confer enhanced robustness. The relationship between model size and stability is task-dependent. We release our full implementation using the Haystack framework and all perturbed datasets on GitHub, so that others can reproduce and build on this work. Let me now walk you through our experimental setup. We selected 3 diverse benchmarks to cover a range of tasks and domain. MMLU tests broad world knowledge through multiple choice question answering. It spans humanities, social sciences, STEM, and other fields. We use accuracy as the evaluation metric here. Squad evaluates reading comprehension through extractive question answering on Wikipedia passages. Here we report exact match, F1, and semantic answer similarity. And Omega is a clinical domain benchmark requiring free-form answers to medical questions, evaluated against physician-crafted guideline criteria using a guideline adherence score. These 3 benchmarks together enable testing robustness across factual knowledge recall, reading comprehension, and specialized clinical reasoning, covering multiple choice, extractive, and free-form answer formats. We evaluated a cohort of 23 state-of-the-art LLMs on these 3 benchmarks. Our model selection covers a broad spectrum. In terms of availability, we include both open-weight and proprietary models. The architectures span dense transformers and mixture of experts' designs. Parameter counts range from 270 million all the way up to 235 billion. And all the models were released between July 2024 and August 2025. We cover 5 major model providers: OpenAI's GPT family, Meta's Llama, Google's Gemini and Gemma, Mistral, and Alibaba's Qwen. All models were tested in a zero-shot setting with temperature set to 0 for deterministic, reproducible outputs. We used the open-source Haystack framework to ensure consistent prompt formatting across all models. Our methodology follows 3 stages, as shown on this slide. In the first stage, perturbation, we systematically alter each benchmark dataset using 2 types of meaning-preserving changes: lexical substitutions, where we replace words with synonyms, and syntactic transformations, where we restructure sentences grammatically. In the second stage, evaluation, we evaluate each of the 23 LLMs on both the original and perturbed versions of all 3 benchmarks, using the task-appropriate metrics described earlier. In the third stage, stability analysis, we quantify the performance variance between original and perturbed versions and apply statistical tests to confirm significance. McNemar's test for individual models, the Wilcoxon-signed rank test for distributional shifts, and Kendall's tau for ranking stability. Let me now explain our two perturbation pipelines in more detail, starting with the lexical one. The goal of lexical perturbation is to alter words with synonyms while preserving the core meaning. Our method is to prompt an LLM, specifically a quantized version of Llama 3.370 billion instruct, to rewrite the input using context-appropriate synonyms. Here you can see an example from MMLU. The original sentence reads, Abraham Maslow proposed the idea that some motives are more imperative to survival than others. In the perturbed version, idea becomes concept, motives becomes motivations, imperative becomes crucial, and survival becomes existence. The meaning is identical, but the words are different. We constrained the model's output with a JSON schema to ensure consistent formatting. For Squad, we added the critical constraint that the answer string in the passage must remain unaltered, so that the correct answer is still findable in the perturbed text. For syntactic perturbation, the goal is to alter the grammatical structure of sentences without changing the words or the meaning. Our method works in two steps. First, we identify possible transformations using dependency parsers from spaCy. We check rule-based applicability conditions for classic syntactic alternations, such as active to passive, extraposition, WH movement, and dative alternation. A transformation is only attempted when its prerequisites are met. Second, we instruct an LLM, again Llama 3.370 billion, to perform the selected transformation. Here you can see the example. The original active sentence is Abraham Maslow proposed the idea that some motives are more imperative to survival than others. This is transformed into a passive construction. The idea that some motives are more imperative to survival than others was proposed by Abraham Maslow. Every single word is preserved. Only the syntactic arrangement has changed. Now let me present our first finding. LLMs are consistently more sensitive to lexical changes than syntactic ones. This bar chart shows the average performance drop across all 23 models for each benchmark. On MMLU, lexical perturbations caused an average accuracy drop of 7.72 percentage points. That is a substantial drop from simply replacing words with their synonyms. By contrast, syntactic perturbations caused a much smaller drop of just 1.64 percentage points. This pattern holds across all three benchmarks. On Squad, the F1 drop is 3.38 percentage points for lexical versus 2.72 for syntactic perturbation. On Omega, it's 1.25 versus 0.54 in the adherence score. McNemar's test confirms that these drops are highly significant, with the p-value less than 0.001 for 22 of 23 models on MMLU under lexical perturbation. The syntactic drops are also often significant, but of a lesser magnitude. This discrepancy strongly suggests that models rely more on surface lexical patterns than on abstract grammatical understanding. When you change the words, the models stumble. When you rearrange the syntactic structure, but keep every word intact, the impact is noticeably smaller. This has important implications. It hints that current LLMs are pattern matching at the word level. Beyond absolute performance, perturbations also alter relative model rankings, which directly challenges the reliability of leaderboards. These slope charts show each model's original rank on the left and its rank after perturbation on the right. Horizontal lines indicate stable rankings, while crossing lines indicate rank swaps between models. For MMLU, the lines run nearly horizontal. Rankings are highly stable under both lexical and syntactic perturbation. But looking at Squad and especially Omega, there are many crossing lines indicating pronounced rank volatility. Models frequently swap positions after perturbation, with some jumping several ranks up or down. Quantitatively, Kendall's tau for MMLU is 0.98 for lexical and 0.99 for syntactic perturbation, meeting our threshold for strict equivalency between the ranks. But for Squad and Omega, tau drops to 0.87 to 0.93. Bootstrapped confidence intervals confirm these rankings meet only moderate agreement thresholds. The Wilkinson-signed rank test further confirms that score distributions differ significantly, with a p-value less than 0.001 between original and perturbed sets for all benchmarks. The takeaway is clear. Leaderboards for complex tasks are fragile. Practitioners should be cautious about making deployment decisions based on narrow benchmark score differences. Our third finding directly challenges the common assumption that larger models are universally more robust. The slide shows the correlation between model size and performance drop under lexical perturbation. On MMLU, the correlation is a strong positive of 0.84, meaning larger models actually suffer bigger accuracy drops. They are less robust, not more. The biggest models, which score highest in absolute terms, are also the most vulnerable to synonym substitution. The story is different for Squat and Amiga. On Squat, the correlation is negative at minus 0.47, and on Amiga it's minus 0.67, meaning larger models are typically more robust on these tasks. A similar task-dependent pattern emerges for syntactic perturbation, with MMLU showing positive correlation and Squat showing strong negative correlation. How do we interpret this? For MMLU, larger models may have more extensively memorized specific phrasings, making them more vulnerable when those phrasings change. To wrap up, our three main conclusions are: first, LLMs can be sensitive to linguistic perturbations, and especially to lexical ones. Simply replacing words with their synonyms can cause substantial performance drops. Second, benchmark leaderboards can be brittle and should not be the only factor in model selection. Small changes to phrasing can shuffle rankings significantly. And third, bigger models are not necessarily more robust. We've seen that the relationship between size and stability is highly task-dependent. Looking ahead, we see three different directions for future work. First would be investigating the difference in performance between lexical and syntactic perturbation to understand why models are more sensitive to one than the other. Second would be extending the perturbation analysis to more languages and perturbation types to better understand the factors that actually influence model sensitivity to changes in the input. And the third direction would be shifting from diagnosing fragility to proactively engineering LLMs for robustness, for more resilient systems that are capable of handling variability in language. We gratefully acknowledge the support from the organizations and projects listed on this slide. This work was partially funded by the EU Horizon Europe project DOOPS, which aims to develop next-generation multimodal foundation models that integrate language, vision, and many other modalities. We also gratefully acknowledge further support from BMBF, the Federal Ministry of Economic Affairs, DFG, and the EU Comfort Project. Our perturbed benchmark datasets and the full implementation is available on GitHub, accessible via the QR code or the link shown on this slide. Thank you very much for watching this video, and please feel free to reach out if you have any questions.